Okay, so just a quick video to talk about images in computer systems and how we represent them. All right, so I think I'll just start off by talking about pixels. Okay, so when you look at a pixel, or when you see the word pixel, all right, I want you to think of the word picture element. All right, and what it basically means is it's the smallest part of a picture. All right, so the smallest part. All right, so you can see in this picture that I've chosen, that I found online, it's kind of made up of dots or little squares. And if I zoom in on that even more, you can see the more I zoom in, the bigger the squares get, because it's a picture made up of a very poor picture resolution, which means that there are not many pixels in the picture itself. All right. So remember, pixel stands for picture element, and it's the smallest part of a picture, right? You can't get any smaller than a pixel in a picture on a computer. And remember, every picture, every image you look at on the computer is made up by pixels. And if you get close up to a screen, especially an older screen with a poor resolution, you can see the pixels themselves. They look like little squares. And like the old 80s style computer games and stuff, you can really clearly see the pixels in them because the resolution wasn't very big. Okay, so what is resolution? It's basically how many pixels. All right, how many pixels in your picture. Now, in the example I've shown you here, you can start off, it starts really simple, being like this is only 1 pixel for this image, and it gets bigger and bigger and bigger until you get to a nice crisp image at the end, and that is the higher resolution one. Okay, so the more pixels you get, the higher the resolution gets. Okay, but if you do have a high resolution, it means that you need more memory because you need to fit more pixels in there. All right. Now, another thing that makes a big difference when you're talking about the images on a computer is the color depth. All right. Now, the color depth is how many colors per pixel. All right, so you have an X amount of pixels here, but for the resolution, but the color depth is how many colors can each one of those pixels store. All right, now the way we tend to work it out is by using this system where we have red, we have blue, and we have green. I know it's not quite red, it's more pink, but you get the gist of what colour each one is. Now, the reason we use these colours is because these are the colours that we can see with our human eye. Alright, now if you actually look at the example I've given you up here, you can see that this image here has a very high picture colour depth, and the one next to it here has a lower one, and you can see on the lower one it actually the water, for example, doesn't really even have any color. Okay, now when we look at this color depth and we look at it in terms of red, blue and green, all right, in a normal everyday computer system, which is 24 bits, it means we set each side of these bits aside for the different colors. All right, so we'll set 8 bits aside for red, we use 8 bits for blue, and we use 8 bits for green. Okay, now what does this mean if we're using 8 bits per color? Alright, now if I draw my binary table like we've been doing in class, 1, 2, 4, 8, 16, 32, 64 and 128 to give us 1 byte of data, or 8 bits, just like we have here. Alright, think about how many numbers we can make using these 8 numbers. Alright, and the answer is we can make anything between 0 and 255. Alright, that's a total number of numbers we can make using 1 byte as 256. Alright, because 0 is a value, remember. Okay, so if we have 256 bits or 1 byte for red, and we have 256 bits or 1 byte for blue, and we have 256 bits or 1 byte for green. Right? It means that if you think back to your art class, when you mix paint together to make colours, we can do the same on a computer using the red, blue and the green. And by mixing them together in different orders or different amounts of each one, we can make the amount of colours that we have if we multiply them all together. So if we multiply 256 by 256 by 256, it gives us just a little less than 16.8 million. Alright, so that means in different amounts, alright, if we multiply the red and the blue and the green in different shades of each one, depending on which shade we need, we can make a possible number of 16.8 different colors, alright, which is a lot. Okay, and some of the gaming PCs and the PlayStations and things like that will probably even have more than 24 bits set aside for color. Alright, but just in a normal PC like we use at school, we're using 8 for red, 8 for blue and 8 for green, which gives us a total outcome of 16.8 or just less than 16.8 million different colors. Right, which is pretty impressive. Alright, so let's think a little bit about files then, file sizes of color and what makes it different. Alright, so the first thing that's going to make a difference about your file size is your resolution. Alright, if you have more pixels, you have bigger file size. The second thing that's going to make a difference from your file size is your color depth. Right, if you have more colors per pixel, it's gonna need more binary numbers, so it's gonna take more file size. Alright. Now, let's have a little look at how we might be able to calculate our file size. And it's quite simple in an image. You just need to multiply the resolution by the color depth. Alright, and that will give you your file size. Alright, I don't want to go into too much depth in this video about file sizes themselves, because we're going to do a whole lesson on that, and I'll make a separate video where we calculate the file size of an image. Alright, so I hope that helps clear things up after the lesson.